Equilibrium. Equilibrium is a very important aspect in any chemical reaction or in any process. It's a state in any reaction or during any process in which what we find that the measurable properties doesn't shows any change in their values. Therefore, at this particular state, we find that the reaction or the process is static. But the reality is that particular reaction or a state is always in dynamism, always some change or the other changes taking place. But what is happening is that the measurable properties doesn't show change in their values. So we define equilibrium as the state in which all measurable properties doesn't show any change in their values. Measurable properties here means the properties like concentration, pressure and temperature. This state, since these properties are not showing any change, is appearing to be static, but it is very much dynamic. We can represent this equilibrium by taking a very common example of a reaction of hydrogen with iodine converting into hydrogen iodide. All these, since are gaseous in nature, they can form an equilibrium with each other when these all are taken in a closed vessel. This sign, which is actually a double half arrow, indicates that there exists an equilibrium in this process or in this reaction. Similarly, we can represent another example of a Haber's process in which when nitrogen gas is combined with hydrogen gas results in the formation of ammonia. Now in this example, we can see that the nitrogen gas and hydrogen gas are in equilibrium with ammonia. Again, the same sign of this equilibrium. Whenever we want to show that our equilibrium is involved in any particular reaction or in any particular process, we will always be representing it in the form of this half double arrows. This equilibrium is mainly of two types. Equilibrium is of two types. The first is called physical equilibrium, and the second one is called chemical equilibrium. Now let us understand the very basic thing about the equilibrium, state of equilibrium. See, state of equilibrium is always associated or is present always in those reactions or processes which are reversible in nature. See, the reversible reactions, we know we have done them in the thermodynamics chapter. We know the reactions can be reversible or irreversible. Reversible reactions are those reactions in which the products are able to form the reactants back under the similar conditions of temperature, pressure and other conditions. So if a reaction or a process is reversible, then only it will be involving the state of equilibrium. I have shown this with the example, like suppose A reacts with B to form C and D. This reaction, I'm putting this sign of equilibrium if and only if the C and D under similar conditions is able to form the A and B back. And such reactions and processes basically are reversible reactions. If the product is not able to form the reactants back, remember the process is irreversible, and under such conditions or for such reactions, we never have any state of equilibrium involved. So always remember, equilibrium is always involved in what? Reversible reactions, in which the product is also able to form the reactant back. So equilibrium always exists in the processes, reactions which are reversible and in which the products always also forms the reactants under similar conditions. Also, the state of equilibrium can be represented in the form of graphs also. Like, let us take the example of the same reaction. Here we have like this is the concentration we can have, and here we have the time. Now, if we since we are starting from A and B, so if we take any of these reactants, we know that initially we were not having any C and D, so their concentrations were initial concentrations were 0, and we were having only A and B. So we are here, so it will be either A or B. As the time proceeds, the concentration of A and B will keep on decreasing. Now here, most of the students makes mistake. Remember, this is which is very important. If this graph, which is following the curved path, keeps on decreasing and decreasing, it is fine. That means till that time, there is no equilibrium. The moment this becomes parallel to the x-axis, it means what? That now the concentration with time is not showing any change. So once this graph, which we see after this point, is becoming almost parallel to the x-axis, it means what? Before this point there is no equilibrium, but after this point the system is at equilibrium. So here this is what for A or B. So always remember, if this such type of a graph is plotted for any of the reactants, whenever till the situation the graph is curved, it's not involving equilibrium. The moment it becomes parallel to your x-axis, the equilibrium is achieved. Similarly, we can represent the same graph for the products also. Initially, there were no C and D, so we are here C or D because both of these are 0. As the time proceeds, their concentration increases and the concentration of the product reactants is decreasing. So their concentration will move like this. It is keep on increasing and increasing and increasing and increasing. Till it is curved, it is remaining curved, it's fine. The moment it becomes what? Parallel to your this x-axis, which we see is happening here. Like here, after this it is becoming almost parallel to this x-axis, system is at equilibrium. So this was for C or D, and this line or this graph remains curved. It means the concentration is keep on changing. So always remember, whenever we have a graph like this or this, the moment these lines become, when it is plotted between concentration and time, the moment the graph becomes parallel to the x-axis, that means the concentration is not showing any change with the time. The system is at equilibrium. We can also represent the same type of graph. We can take a much simple example in this way also. Like suppose A is changing into B. They both are at equilibrium. Now what we can do, they attains equilibrium. How we can represent this state of equilibrium between A and B in the form of a graph? Like concentration and time are taken as the coordinates. Now here initially we were having only A, and initially the B was 0. The concentration of A goes like this, concentration of B goes like this, and after this what we find is they have the same concentration. So it means what? Till this point is achieved, this is A, concentration of A, this is B, their concentration of B is increasing, concentration of A is decreasing, but after this point their concentrations are not showing any change with the time. It means what? This is the state of equilibrium.